So there is still a little bit of overlap with what we are doing in 2310 at the moment in parallel, but we will quickly actually diverge now and go into a lot more advanced territory here in the real-time course. Still, I need to have everybody on the same page. So I need to go through some material which you may have seen earlier. We are diverting now from the basic sequential stuff slowly into a little bit more programming for grown-ups. There will be a lot more advanced material and topics in the rest of the programming today. Okay, do you still have any questions from last time? Do you remember last time? Maybe you remember later. So, first one is something that should actually come completely easy for you guys. Template programming, generic programming, polymorphism, that's all nothing that should be surprising for you at all. The students coming through the ANU, you all have seen this from first semester on. You've all seen parametric polymorphism straight out. And the ADA version is a little bit more complete than what you're used to in, say, Haskell or programming languages like that. And you have the full range of generic possibilities. You can make pretty much anything generic, and any combination of features is possible. You're not dependent on being generic with respect to type classes a la Haskell, of classes a la Java. You can make generic objects based on any kind of combination of operations. So you can say this is a private type. I'm not telling you anything further specific now. Let me refine a little bit. This operation exactly exists for that type. You can be as specific as you like for that. If you say private, what does that mean? In that context, it just means that this is a generic type where I'm actually surrendering no information whatsoever about this type. This is a generic package which works for any possible imaginable type. Does that make some sense? Well, if you have a queue of something, you're never actually doing anything with this queue besides that you have to be able to copy any instance of this type. As long as this is okay, so it's not a limited private, it's actually just a private, then you can, of course, queue anything. Right? So that makes sense. This is exactly what you would do in Haskell by not putting any further qualification on this whole thing. Bit of an idea what else, to broaden your mind a little bit, what else can you make generic in generic programming. And the last two are the ones which are rarely seen in university code, in education code. And this is that you can make generic interfaces, generic entities, also dependent on other generic entities. So you can hand over instances of another generic package as a parameter to a generic package. Am I confusing you, or do you have any idea what I'm talking about?
So basically it's like having queues?
No, not the same one. You can have, I will show you examples of that in a moment, how to do that in practice. You see this in real industrial code plenty, that you instantiate some base category, some base instance, and you use this instance to instantiate further classes, you instantiate further instances of that. Why do you see this comparatively frequent in industry, this kind of pattern? As opposed to what you're used to at university, where you mostly use the opposite direction. You're breaking it down top-down in much finer granularity stepwise. Yeah?
Would it be that if you can certify sort of, one of the small parts of it, then that bit works for whatever instance you've got?
Yes, that's related to that. The fact is that if I instantiate at declaration time, if I instantiate a package and then hand over this instance to another package, all what I'm doing here, all what I'm talking about here is completely static. There's no dynamic operation involved at all. This looks very dynamic in terms, it looks quite similar to, say, object-oriented programming, but you don't leave any questions open. You instantiate this once and for all and in full. And hence, this is the usual pattern which you see industrial code, which A, has to be predictable or otherwise certified, because then you can, like you hinted, you verify this one package, and then you instantiate that one, and you know exactly what instance that is. The other aspect of this one is that if you have a generic package like this is only the declaration part, but if you look at the generic code part, can you generate code directly based on this package? So keep in mind, it's a generic package. This is not an actual package. It's a generic package. The type which I want to use is not yet known. Can you nevertheless already generate code for this? Would you expect your compiler to already generate code for this at this time? Yes?
I mean, it would be currently executable, but it could be something that could be linked, like called by another.
Mm-hmm. Or to ask the question a little differently, if you instantiate a generic package like this 5 times with different element types, would you expect your compiler to produce 5 different pieces of code, or one piece of code which is using some reference to a generic element? I have the class split. Great. Why do you think no?
Different variables, different types will have different sizes. So, for example, you need to allocate different amounts of space in the stack.
Pointers. I just use a reference.
That's less efficient.
It's insufficient?
No, less efficient.
It's less efficient, okay.
Because you've got small types passing
Yeah.
like an 8-bit integer around.
But I don't have to run my compiler for 2 years because I'm only producing this piece once.
You might be able to do, like, is full, doesn't depend on the size of element. So you could only have, like, have
Sure.
one for that and then multiple for the other one.
Yeah. The interesting question is, as a compiler constructor, would you be able to choose? And the answer to that one is yes. You could actually decide this, whether you want to generate less code by having a single piece of code which addresses that, or you want to have more optimized code by getting rid of all the references and just hammering it all into flat arrays of a specific size, rather than arrays of pointers. So not going Python style, but actually nailing it down in concrete arrays. But then you have to produce fresh code for every instance. Right? Your Ada core system does that. It chooses to produce new code for every instance, which makes it more performant, but makes the code bigger. Right? Other languages don't have that choice. In C++, you can't do that. You actually don't have the full information at this time. You need to wait for an actual instance before you can produce code. Yeah.
If you have 2 instances of the same element type, would it produce one new code, or would it produce 2 separate, even though it's the same element type?
I would strongly expect it produces 2 separate codes. That goes together probably with the namespace and the type system in Ada. Because the type system in Ada is by name, not by structure. So you will find this plenty, and it's quite annoying if you fight against this at some point. You declare 2 structures which are actually absolutely identical in 2 parts of your code, in 2 separate aspects of generic instantiations. You know that they're 100% the same piece of code, but they have a different name, or they're in a different scope. And Ada is absolutely blocking that. There's no way to go around that one. Types are matched by name, not by structure. If you cannot make the names match by some shuffling in your code, the type system is absolutely strict about that. And hence I would strongly suspect that Ada is not looking for any kind of optimization here and not mapping the code even if it's the same code. Okay. This is the pattern how you instantiate that, as opposed to the ADA text IO, where you just say, give me ADA text IO and dereference the namespace straight away because it's already in existence. For a generic package, you can't do that because it doesn't exist yet. You have to instantiate a generic package first before you can actually use it. So first we just import that one, and then we instantiate one. QPack positive, we're just providing a new type, and then we can use it. And the rest is simple. Okay. Feeling familiar about programming by generics? Yeah.
Where can I choose whether it's using the same source file?
You can't. You can. That's the ADA specification says that this is a choice up to the compiler constructor, not to the program. And logically, it doesn't make any sense. Both is predictable. It's just performance differences and size differences in terms of code. This is not in your control. This is a choice for the compiler constructor, not your choice. Okay. Cool. Nothing else. So now we actually have to go for concurrent programming, which for almost everybody of you should come completely easy. But let's just step through that quickly. Just doing another generic one, but there's no miracle behind that one. And those are the instance of the protected objects, which gives you a frame mostly for mutual exclusion, and at the same time also to give you a possibility to distinguish between readers and writers, which you need to be able to do. Do you remember how this thing distinguishes between readers and writers? Yeah?
Is it that a function is always going to be non-side effective?
Exactly. The functions in that context are defined and forced to be non-side affecting. If it's non-side affecting, you don't have to worry about concurrency and race conditions because they don't do any damage anyway. Which means you can leave as many processes using these functions at any time as you wish, but you then have to keep all the side affecting operations out while they're all in there, and vice versa. You have a single side affecting function in there, a side affecting operation, not function, which is a bit irritating, a single side affecting operation in there. Everybody else has to be out, including the side effect free functions. Okay. Procedures are the most primitive one. This goes back to the 70s, basically. This is, you put this into a block, and back in the 70s and 80s, this was called a monitor. If you still remember this, if you're old enough to have seen those kind of structures. And you're just collecting a number of operations in a single block, called as a monitor, and automatically all operations in there are mutually exclusive, and you are delivered. Functions, side effect free, you don't have to worry about too many processes using them at the same time. You can have as many as you want. And then you have the most powerful option here, the most interesting one, the entries. They have waiting queues associated with them and predicates associated with them. So you can have now operations which are dependent and only available if a specific predicate is currently true. If not, what do you expect to happen? Say again?
It does something else or comes back to it later.
No, it does not do something else.
Also,
So if you as a process call enqueue here, and this enqueue operation says, my queue is full, there's no queuing here at the moment, what do you expect to happen to you? Why an exception?
Because that's an error, you shouldn't be enqueuing with full.
That's exactly the beauty of concurrent programming. You don't have to raise an error in those situations. Right? Why would you raise an error in those situations? In a sequential program, you have to raise an error because you cannot not ever get out of that.
When it's deadlock.
No, it's not deadlock.
Well, you could have a deadlock if everything's blocking, waiting for the queue to finish, and no one realizes
Sure. For that, you have a bit of deadlock analysis up your sleeve to actually make sure that this doesn't happen. And part of that is actually part of the compiler already. But the general assumption is, in a concurrent program, an entry is closed, it's probably going to open eventually. Right? And in a concurrent program, this makes sense. Because if my queue is currently full, but I know I'm just part of a large process system here, and I have other processes which are taking stuff out and putting stuff in, then eventually somebody will actually take something out of the queue again, and bingo, here I go. Then I can continue. So I'm just delaying these tasks until somebody else can do something useful with my protected object, and then I continue again. So I just reshuffle the order of execution rather than pressing the panic button and stopping everything, what you would need to do in a sequential program. Right? That all make sense? Cool. And those are very simple, just the predicates which we have there. And instead of now pressing the alarm button and you're raising exceptions or having contracts which are giving assertion violations or any sort like that, we're just saying, if this is currently not possible, patience, young Luke, we will come to that. Right? We're just slowing people down a little bit. Is that leading to, yeah?
Two different processes calling queue, and they're both blocked. Is there any order to which one gets access first? This way.
Good question. What do you expect in which order processes are being executed? First in, first out. Yeah. You have actually control over that. The queuing policy which you apply to these kind of protected objects is actually in your programmer's control. By default, you have the queuing policy FIFO within priorities. So you order your processes according to their priority and then according to arrival time. That's the default, but you can change that. The underlying criteria is it must be predictable, which means you need to have a controllable order of some sort. So random would not be a cool idea, because if you have random, then you can never guarantee fairness of any sort. Because if you have random, it could mean that one task is desperately trying to get in there for half an hour, but there was always some competition, and Ada always picked the other guy. That would be random. So that doesn't make sense. Yeah.
Isn't it the same if there is a queue based on priority and on order of arrival?
Yeah.
Then if there's always a higher priority thread incoming to the wait, there's a chance that we'll have starvation from the lower priority.
Yes. But you have that anyway if you have a priority-oriented system, because you have only a limited number of CPUs. So if you have, for example, currently 5 high-priority tasks runnable, too bad. All the lower priority tasks will starve. So the difference, and this is a big difference actually between a real-time system and a desktop operating system. It's one of the major differences, as a matter of fact, that priorities are taken religiously serious. If you have a higher priority task runnable in a real-time system, it will be preferred under all circumstances. There is no consideration of fairness with higher and lower priority tasks. A higher priority task has a higher priority. It will always take precedence. If you have a system built around lots of higher priority tasks, which are always runnable, you just messed up your design. That doesn't make sense. You cannot rely on the fact that there is some underlying round-robin fairness distributor which occasionally gives a little bit of CPU time to everybody, so maybe a little more to the higher priority task, a little less to the lower priority task. This is not what happens in a real-time system. Because the consideration of fairness in terms of everybody gets a fair share, this consideration of fairness if you think about this for a moment, doesn't make any sense in a real-time system. Why?
Because if a process is trying to give you a guarantee on the time that it will take to complete, then it needs that specific amount of time to run the processor. And if there's a high priority task waiting to run, then it means that it's within that time period. And beyond that, it's not going to request to use the processor, so then it will yield to lower priority tasks. So if a higher priority task is able to run, then it needs to run, basically.
There is no notion of everybody should have a little bit of a fair share of a CPU if you want to keep within deadlines. You have a current task which has to run until its deadline, or it has to run until it's suspending itself voluntarily. And what would be a justification to ever interrupt this task? Because you have to imagine every interruption, every context switch makes your life harder. Every context switch is harder to calculate. What does that mean in terms of predictability? How many random fairness context switches do I need to calculate in order to calculate my worst case runtime? None. You only have to calculate how often can I be interrupted by a higher priority task. And this is not a question of occasionally, so every five times a second you're going to be a bit interrupted by a higher priority task. No, if there's a higher priority task, you are down. And it runs to completion or to the next synchronization point, and then you're coming back. So your scheduling calculations will become a lot easier. Okay. If you have everything on the same priority level, this is also an interesting one. What happens? How often do you switch tasks? If you have everything on the same priority level, when do you ever switch tasks, assuming you have only one CPU now for simplicity for a moment?
When you want to.
When you what?
Want to? And when the president.
When you yield, when you actively say, please kick me out, please suspend myself. Yeah, would you ever say that? Why?
Okay, well, if you're running something like a downloading a file from anything, you might want to just suspend.
From the perspective of every task, you have to fulfill a certain deadline. You have to fulfill a certain task. You are done. You're suspending yourself when you're done. It's not that these tasks are usually running on a continuous basis and taking as much CPU time as they possibly can because they have a job to do. They have a result to deliver. They deliver their result, then they suspend. So when they go to an I/O operation or they yield voluntarily, those are the only points when you will see a task change in a real-time system when everything has the same priority. Okay.
So there's no preemption with the temporal systems?
Of course there is preemption.
And preemption due to time slots to timing out?
No.
No, there are no time slots.
Well, there is, we'll talk about this in some finer granularity later. There are a few fine exceptions to that. The general notion, no, but there could be unpredictable transient user tasks of some sort, which you need to consider in the overall scheduling. There are some special tasks which are a little outside of that. For all the control tasks, there will be no time slot-oriented preemption. There is, of course, preemption in terms of a higher priority task becomes runnable because of an external event. There is, of course, preemption for the lower priority task. Yeah?
Do you see much cases where they have exactly the same priority for all tasks? So imagine you can surely work out some ordering, even if it's not a sort of linear ordering of all of them. Each one could be a function of, oh, that one's done, that's not done, and I'm going to be more important than this task, and you can just do the maths and work out who's most important.
interesting question. As a matter of fact, you see this more often than you think, because the association of priorities is actually often not that important with respect to making sure that the total time, all of my control tasks or result-producing tasks can be scheduled on my CPU, and they will all get their work done. And actually, quite often, you do not really care in which order they're doing that. As long as you guarantee that they all have enough time to deliver their result, you actually leave it open. Because the fun thing is, it sounds so easy. You give the important parts, the important tasks, the higher priority, right? That was the easy part. Next part is, which of those tasks is important? And you will find that these questions are much harder to answer in practice than you think. Give me an example for an important task.
Turning off when the thing's about to blow up. If it's about
yeah, that's correct. And that's more or less the easy part. If you actually know that if this task does not run in the next 2 microseconds, I'm going to explode. Cool, yeah. Bit of a cartoonish example, but yes, you have these kind of situations where you know that this is a situation where if I'm not running this task, my thing is going to burn down. And you will give this thing a slightly higher priority task, because otherwise there won't be any other tasks after that. But you will probably also agree that those are fairly rare situations where you can point at a task and say that this is not running, I'm going to explode. Yeah?
Depending on the main task is waiting for some other task to be like so one want to put the other task as a high priority so you can consent with that.
We will talk about this when we talk about the synchronization and the communication between tasks. This is what you're referring to now. And we have to talk about what it means to synchronize between tasks, and particularly between tasks of different priorities. Or, to put it the other way around, if tasks on different priorities are using the same resource. So they're blocking on that. If I'm claiming a certain resource and I'm currently inside this resource, and this is, for example, a protected object, this is a hardware operation which I have to go through at the moment, and this is uninterruptible, because I have to complete this hardware operation, and the higher priority task can bath in the sun that it has a higher priority. Doesn't help, because the lower priority task, has claimed a bunch of resources at the moment, and you have to wait until these resources can be sensibly released.
in that case, like the high priority should be inherited. I mean, the low priority holding the resource.
Yes, that's the naive approach to that, to use priority inheritance. And we will demonstrate later in the course that priority inheritance does actually not work. It sounds very tempting, and it doesn't do diddly squat. It makes the lower priority task feel better, because then the lower priority task knows I get my high priority inherited the moment I'm getting requested by a higher task. It doesn't speed it up. It's still the same task. It doesn't change the overall sequencing much. There are specific situations where it works. In practice, most of the time it doesn't. And there are much better versions to do that. This will be, if you want to look it up, this will be around priority ceiling locking mechanisms. And these priority ceiling locking mechanisms are comfortably actually already part of your Ada runtime environment. You can switch that on directly, and you get this kind of synchronization automatically. Cool. So you're all familiar producing a bunch of tasks, a bunch of concurrent entities in Ada. Supposed to other languages, this is all very short, usually producing some tasks in Ada. The only thing you need to do, you write down usually some task types, because you want to instantiate a bunch of them, not only one. And then you say, I'll make this very simple here. You have just an array of 3 of these producer tasks. You have an array of 3 of these consumer tasks. And in these 3 dots here, we have to declare what's the code actually of these tasks. We'll do this in a second. And then we say begin, null, end. Why do we say begin, null, end?
Waits for the task to finish, right?
Yeah, but why do I say null? Exactly, because otherwise the compiler bugs me. The compiler bugs you for code maintainable and pedagogical very valuable reason, because we're usually writing our stuff down in some framework and we leave the implementation parts for a little later. So we have lots of curly braces or begin end blocks where I will fill the code in later, right? And the error message which you get here is, well, there's an empty begin end block. Is that on purpose? Did you want to fill in later something? Or did you purposefully leave it empty? And hence you write null, which means, no, that's on purpose. That's supposed to be empty. Okay? How do you start these tasks? How do you get them actually going?
When they create it.
Already running. Nothing to be done. Right? Just declare them. The strict language specification, if you want to go by the books, says that by the next begin statement, all these tasks will be running. It does not tell you how early before that they're running, so they could start running any time between these declarations and the begin statement already. And the order of instantiation is also not defined. So they will be just running before this begin statement, and that's all you need to do there. If you need to synchronize your tasks, please don't rely on your runtime environment to synchronize your tasks in any fancy way. Just synchronize them yourself. The first thing in your task, if you have to synchronize to something, is a synchronization statement, and then you do that. But you have to do that yourself. If you don't do that, it is assumed this is just a decoupled task, which can run straight away, and it will do just that. Okay. That was easy. Bunch of tasks. Okay, let's produce these tasks. Here's the producer task. It does 2 statements in a loop, not particularly spectacular. Just define a subtype of characters from A to F, and then I have a for loop for all of these characters in this range A to F. And I make first a little statement on the terminal, what's going on, to keep you entertained. That my current task is checking out the queue, and it checks whether the queue is currently empty, it checks whether the queue is currently full, and says so and prints on the terminal, and then it queues it up into this protected object. And calling on any kind of a synchronization operation, which is message passing, shared memory synchronization, any synchronization operation imaginable, you always have to add manually in your head the comment behind it. This is potentially a blocking operation, guys. You call that, you have no guarantee that this will go through. It's a synchronization task. If the synchronization is not successful, you are going to be suspended right there. Always have to read your code like that. Yeah?
It's not stupid, but is the test body ESM1 as the test type?
The test body as a task body as a task type? Yes. 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 They can be spread over specification, implementation part. If you want to use this task type in another package someplace, then you have the task type in the specification part and the body somewhere in the implementation buried. So you spread it like that. But if you want to have just a task locally, then you have it just sequentially. Specification and implementation straight on. Cool. And when we send out all of our characters, we say that this task terminated. And for the consumer side, we do almost the same thing. For the consumer side, we call dequeue, get one of these characters out of the queue. Then we count our internal counter up happily to make sure we keep log how many elements we got out of there, and then we produce a similar line for entertainment on the terminal, which checks again. Now, after I got this out, is the queue now empty? Is the queue still full? And if I get the last character, this was a range from A to F, so if I get an F in my queue, I'm going to commit suicide and terminate. So if I get an F out there, I break out of this loop. This is like you're used to from C-level C programming languages, like a break statement. You're getting out of a loop someplace in the middle of it. Okay. And you say again, this completed. How valuable will the terminal outputs be? Test run here. Does that make sense? Do you see on the screen here? The order how this is executed, we are not running this at the moment on a real-time system. This is running on a desktop system, which means that the order of these tasks is completely unpredictable. But what do you think about, yeah?
So what schedules the tasks on the desktop?
Depends what version of the Ada environment you're using there. You could run into a situation where Ada is actually scheduling the tasks in its own runtime. So to speak, it implements a local threading library inside its own process runtime. Or it uses the processes from the operating system to do that. And on your machines, the latter is the case.
So they're running these processes?
Say again?
So they're running these processes?
They run as processes, yes. And, well, no, not necessarily as processes. You can also run it as operating system threads. Right? But the point is the scheduling is not really in your control if the Ada running on a desktop operating system or on a laptop will use the underlying process or threading library, because then you're dependent on the schedule of the operating system to do that. But what do you think about task receives a character and the queue appears to be full afterwards? How can I take a character out of a queue and the queue is full afterwards? You all should see that. Sure. I didn't lock anything down in that process. There is time between me actually taking something out and me looking at the queue whether it's still full. And I have a multi-core environment here. There are at least 4 other processes running at the same time. Nothing is stopping you from hammering more characters in the meantime between me taking something out and me asking whether the queue is still full. Yeah? No. Don't think it has anything to do with caches. It's just simply the question, if you look at these code sections here, you're queuing something out, and then, God knows what, you have 5 other processes running in the background, which all can hammer at the queue at any given time, and then you're calling the queue operation twice. You call queue is empty and you call queue is full as separate calls, which means you could also have the answer on the terminal here that I got a character out, and afterwards the queue is empty and full. All right? You all see that? Okay, so that's important. That's discouragement. If you want to live and work in a concurrent and particularly real-time environment, just putting sequential messages on a terminal is not cutting it. In most cases, it's more confusing than it's actually giving any useful information in the process. Okay. Any further questions at the moment? That should all still be fairly easy. Okay, cool. So let's do some message passing, because I'm sure most of you are familiar with the concept of memory synchronization, but not all of you are familiar with the concept of message passing. That's a different story. Can somebody outline what's the difference between message passing and memory-based synchronization?
Not sure there's one by copy.
No, that's not the point.
You don't specify how the message is actually delivered per se, just waits to get it. The message transfer and sending it, where the memory you have to put it somewhere specific.
Think a little different. All of these operations are ultimately synchronizing operations. Right? If you do a message passing call, or you do, we're talking synchronous message passing here, of course, we are talking real-time systems. If you do a message passing call, or if you do a call to a synchronized memory area, this is all synchronization operations. What are you synchronizing to in each case? Now, in the case of the memory-based synchronization, what are you synchronizing to there? Say again? To a lock?
I mean, like, to the machine itself, not communicating between machines.
Yeah, sure, yes. So, but think about message passing locally for the time being. Yeah? You synchronize it on a lock somewhere. So, for C fans, ultimately you synchronize on a semaphore, you synchronize on a lock of some sort, right? This lock is an active or a passive operation. The lock is active. It's hopping up and down in the background while you're not looking. No, it doesn't. Right? While you're not looking, the lock is just sitting there. The lock is operated by tasks. So a lock is only changing if a task is actually doing something with these locks. Right? So you're synchronizing on a passive entity, which you use to synchronize a specific area of memory. Okay. What do you synchronize to in terms of message passing? You synchronize with another process. And that's a very different kind of thing. You have to synchronize with another process, another active entity. How can this happen? It can only happen if this other process, this other active entity, is happy to do so. So you have to have the collaboration of this other task. Only if the other task wants to exchange messages with you at a specific point in time, you can synchronize with that other task. And then actually both of these tasks are synchronized, hence it's called synchronous message passing, and you can exchange messages. So it's a very different form of synchronization, and one is called message passing, and the other one is called memory-based synchronization, or protected objects, or monitors, or whatever you want to call it. Right?
You could do synchronous memory operations there.
The memory operations are always synchronous.
No,
but it's with a passive object.
Implement some kind of message passing using memory things with locks.
Then it's not synchronous. You still have to have the other task. Well, okay, yes, you can. But the end result of that is still that both tasks are synchronized. How you get in there in the intermediate stages is an implementation issue, but the ultimate result of that is still that both tasks are synchronized. Right? So that means if I have a task type, which is a bit more interesting than the task which you saw before, so those tasks have entries, and here you see one of the funny features of Ada, namely that it scrupulously reuses keywords left, right, and center for all kinds of different purposes. Because here it's an entry. You have seen entries just a few slides ago, right? You have an entry in a protected object, and you have an entry into another task. They sound very similar, but the difference is exactly what we just said. An entry into another task is a synchronous message passing operation. An entry into a protected object is synchronizing with a passive object. Right? Can you imagine why Ada is such a beast in terms of constantly recycling keywords. Say again?
It's got so many of them, it would be a nightmare to do it.
Well, this is what they're hoping you believe. But what's the actual reason? The point is that this is a very long-term maintenance, very slow maintenance cycle for software, and you have a lot of Ada code which is 20, 25 years old, and this is actually still running exactly as it has been running 20 years ago under the same compilers today as well. And this can only happen if with every new upgrade of Ada they're introducing the smallest possible number of additional attributes and keywords, etc., because otherwise you would invalidate identifiers. The moment I introduce a new keyword, that means this keyword is taboo as an identifier in my programs, and I have to refactor all of my code again. So I'm trying to avoid this like the plague.
Did they have a reason not to just at the beginning to put a whole bunch of keywords just at the side?
You could just make the syntax different, like put a dollar in front of variable names or something like this.
Dollar in front of That reminds me on the worst parts of my childhood. Dollars in front of variable names. You know where this comes from, right? Dollars in front of variable names.
I started in PHP.
Yeah, it's exactly, and PHP learned it from BASIC, and this is where this kind of naming scheme comes from. Unfortunately, you still have languages today which have all kind of crazy characters in front of their identifiers to make different classes and kinds just by the identifier name. Okay, let's not try to get there. So, we have now entries into tasks, but how are we servicing them? This part of the task is still same, just define the data structure internally. This is the same as what you would have had in the protected object as the local data structure. But here comes the interesting part. You're all used to select statements. You may not be happy about them, but you're all used to select statements. And select statements are actually a fairly easy and clean operation. It's not as messy as you're used to, because if you use select statements from, say, POSIX environments, then you probably go, it's not one thing I want to do at a late time at night. But from a conceptual point of view, select statements are not problematic. What is the semantic of a select statement? What does it express?
POSIX or Ada?
In both, actually.
It's the same, semantics are the same.
Yes, but the possibilities to actually implement it right are a little easier here. So in the idea and the semantic is the same. The point is you have a lot more pitfalls if you do it in POSIX to get it completely wrong.
Can we select statements cascade in Ada like in C?
You have select statements inside select statements?
No, when, for example, when you find a label that matches the switch criteria, unless there's a break statement, it will continue to the end of the fall through. Yeah, fall through, exactly.
You call this a concept?
It's useful many times to optimize many things.
Really?
Yeah, it does.
You use a lot of bugs. You remember the SSL bug, the recent SSL bug? Yeah, that was exactly that. Somebody forgot a break in the wrong spot and unfortunately invalidates the whole program protocol, but yeah, it's very useful in some situations, right? No, actually I'm quite glad that this is history. Even C# eliminated that. I mean, you will not find any self-respecting language which has been introduced in the last 15 years, which still has fall through case semantics or select semantics. Okay. I think that's about the same level of using gotos. Having said so, Ada has gotos.
So does C, and they're used pretty often. Set jumps are used.
Yeah. Yeah. It's a funny discussion actually. And most languages have first the reflex of go-tos, no. And then there's a more serious discussion about, well, there are a few cases where, so yes, most languages, even though most people are not really aware of that, do have go-to statements, but not fall-through case statements. That's really history.
Do you have a computed go-to statement that you can use instead? Like go-to an expression that's not a constant? When you work out that runtime?
I don't think I've personally ever used go-to. No, I do have actually a go-to statement in one of the embedded systems, but this is an absolute statement. So I don't think I've ever seen a non-absolute go-to statement in Ada. You mean a go-to with an expression behind it?
Yeah, which is basically what a switch is in C.
You guys are brave. Okay, now let's not talk about all the damage which has been done in the early 70s. Let's talk about what a select statement actually is if you use it right. What's the semantic of it?
Branch to one of the branches based on the condition.
That sounds like a case statement.
Yeah, which is basically what it does.
No. If you use a case statement, then use a case statement. A select statement is a different thing. It does that non-deterministically, yes. Based on what? No. Not on the guards are cool, but that's not the core.
So positive selects lets you add in file descriptors until you can read or write to them.
Yes, and file descriptors are what?
Sorry?
File descriptors are what?
Like sockets or files on disk. Or
Sure, I know, conceptually.
a number of integers.
No, conceptually.
So you can handle to a file.
It's an I/O operation.
Sorry?
It's an I/O operation. It's a communication with the external world. That's different from a case statement. You cannot have your case statement dependent whether you have traffic from outside. It's exactly where you need a select statement. You can only use select statements for that. Case statement is a static expression where the branching depends on the current state of your program, not of any I/O. Right? So you have, and this is by definition of I/O, automatically non-deterministic. Otherwise, you would control the world if you would know the deterministic order in which you get I/O. Right? And the syntax for that is, of course, again, part of Ada. And here you have examples for select accepts, which is the most simplistic form of using a select statement. You will see more entertaining ones when you come to asynchronous select statements. And select statements which allow for timeouts and asynchronous interruptions, which is way more complicated and doesn't work in POSIX. Here's the basic stuff, which has select accepts with a guard attached to that. So that means this accept is only open to the outside if this guard is evaluating to true. Right? Easy. And in this case, we're using the guards same way how we have been using the guards in a protected object to make sure that you're not calling on this protected object if it's currently not making sense, or not enqueuing something into a full queue. And this task, which manages the queues, is not offering its accept statement to the outside world. It's not willing to synchronize with you if the queue is currently full. Where you're ending if you call on this accept? Of course, the task need to be blocked again. If you try to do synchronous message passing with some other guy, and the other guy refuses, you have to be somewhere, and you're being blocked. Which means for every entry in a task, you also need to implement automatically a queue so that you can be suspended and blocked on that one. What happens if all of these conditions, what happens if this thing would, that is full and empty at the same time is obviously not very reasonable, but you can imagine that you have a set of predicates and at some point, they're all closed, they're all false. what do you do then as this task? For what? What are these predicates dependent on? Say again? What are these predicates made of?
Well, I mean, if it's both full and empty, kind of a little bit.
Sure, that's confusing, but forget about that. It's probably not going to be full and empty at the same time. But assume that all of your predicates which you're using there are all evaluating to false when you, as a task, come over this select statement. You can imagine that. What do you happen then to this task? Say again?
It's like only affected by like the computation of this task.
Yeah, just do nothing.
Like they're not going to
Do nothing?
Yeah.
How do you do nothing?
Just like go, there's a loop, just go to the next iteration of the loop.
Doesn't really help you because the predicates are still false.
So you loop infinitely?
You loop more, which means your predicates stay false, which means you're looping infinitely on a hopeless situation. It has to actually break. It actually has to raise an exception because this is a program error. If you design your predicates so that there is a possibility that they're all false at the same time, this is nothing but a program error. Because if they're all closed and all of these predicates depend on your local own condition, there is nothing sensible you can do about it. You're just doomed. When you raise an exception, well, what happens to this exception is, of course, a different story then. Whether you catch this exception somewhere else inside this task. We talk about exception handling and tasks a little later. How do you do that sensibly? Yeah.
What's wrong with having them all waiting on conditions? You could have, I don't know, some...
It's only affected by the computation in that function, so they'll be waiting for some pattern.
Because the internal data is never going to change. But can you have another task changing some conditions or something else?
Exactly not, because this predicate can only depend on local information inside the task. This predicate cannot be dependent on global data someplace. Because if you really depend on global data someplace, you're in hell anyway. So Ada will forbid you that for starters.
You could also have an else statement, right?
That's cheating, yeah. You can, of course, have an else statement built into your select. So if currently there's either everything is closed or that there's no I/O happening at the moment at all, then if you have no I/O happening at all, but some of them are open, then you wait, like in a POSIX select, you wait until the first operation comes in, and you take that one. But if you have an else in there, you're not patient, and you're only checking, is there something on the I/O lines at the moment? No, do something else. Go directly into the else branch. Yes, that's syntactically possible as well. We'll discuss that a little later. Cool. And then you get the actual accept statements. And these accept blocks are begin-end blocks for a very good reason. Because those accept blah, blah, blah end blocks define exactly the synchronization parts between two tasks. Task is calling on this one, and you are keeping this calling task in limbo and in synchronization until the end statement here. You control that. You control how long you keep this task in synchronization. This is particularly useful and used if you want to return messages to the other task in the same go. So you receive parameters from the other task. This is the first message. Then you do something inside your accept end block, and you can have out parameters in that, and they're being handed back when you run over the end statement here. So you control that again. Very different beast from memory-based synchronization. This is message-based parsing. And then what you do inside is decouple from the other task. So this is past the end statement, I see you. This is past the end statement. And then you just do the maintenance locally to your queue, which you need to do. Yeah?
Is it possible to have a task enter in queue before 3 is updated?
before free is updated.
Yeah. So before you start into the highlighted part, another task enters thank you.
No, there's only one task here. So keep in mind, this is not a protected object, this is a task. So everything what you see here is sequential. You actually have to go in a loop again back and have to go over the select statement again before you can accept another task. But there's a related question to that one. Can you accept another message while you're currently in a rendezvous, in a synchronization with another task already? Can you accept more messages while you're currently in synchronization? And the answer to that one is yes as well. You can do that if you like to. There's a pretty clumsy way to actually combine multiple tasks. Yeah.
With this implementation, would you, so say if you had quite a few DQ operations, for example,
yeah,
and no NQ operations coming in, would and you also didn't have a full list, would it not go to DQ any of these? Because, is full would evaluate to, false. And so it would go accept NQ. And since no NQ operations are coming in, would it just block? Okay.
This is actually not deterministic. Yeah? You have no control over that, in which order this is being executed. Then you have another bunch of accept statements. This is nice ADA comfort, which doesn't work in distributed systems, but it works on local systems. And that is you can have an select or terminate. This is a classical pattern for a service task. You want to offer a number of ports to the outside, but at some point, if you have, not typical for real-time systems, but for many other systems, if you want to ever shut down your system, you have often a cascade of bingo. You have often a cascade of servers which all have to be shut down. Is that because I wait too long? Which all have to be shut down. And how much code do you have to produce to power down all of your servers? Have to find out, is everybody else gone? All the other clients are powered down, all the other clients are dead. Then I can close down my server as well. A semantic of the select or terminate is that if there is no syntactical possibility left, all the other processes which could syntactically ever call me are terminated, then the select triggers, the terminate triggers, and you terminate this task as well. So you have a very, very simple way of just killing all of your tasks, the whole task hierarchy, just by adding if there's nobody else around which could ever use this thing, shut it down. Yeah?
Doesn't that depend on having sort of dependency tree?
Yeah.
Then if there's any link to all this
Yes.
space?
Yes. Yeah. This only works if it's strictly hierarchical, of course. Yeah. But it's not too untypical. Okay. So, and then you can actually use that. Here's an example. The lower part is interesting for you from a real-time perspective. Instead of select or else, which means you have zero patience, there is nothing coming in, you do something else. You have also here the possibility for outgoing calls to put it to a timeout. You say here select, DQ, or delay by 1 millisecond. And if this call does not go through in 1 millisecond, which is of course a very long time, then you power this whole thing down. You give up. Very simple way of programming a timeout. So, but we cannot do distributed yet. So this is going to be rough. But you are solid, well awake, experienced professional programmers. Why are you looking so funny? Okay, so that's a bit more interesting. Now I'm mixing a lot of things all together. I'm mixing generics, object orientation, dispatching, message passing, select statements, all in one shot. We start by having an abstract interface. I'm now making my queue type, a queue interface, which I call synchronized interface. And the only thing which is defined on the synchronized interface is a procedure enqueue and a procedure dequeue, which are both at this stage abstract. What on earth does that mean? Synchronized interface means that any implementation of this queue, this is only a generic abstract package. It really doesn't exist. It really is only in your mind. Generic abstract, somebody has to actually do that, do an instance of that at some point before it becomes real. But if you plan to have a real implementation of that one, it has to be a synchronized implementation, which means you're only allowed to implement these procedures here by operations on protected objects, which are synchronized, or by synchronized message passing operations. Those are the only syntactical allowed implementations of this interface, which I have here on the screen. So, and then you can implement this with tasks or with passive objects, how you prefer that. Okay. Abstract methods also force you to explicitly override them. You inherit from that, or you create a concrete instance, you have to override them. So far, so easy. Now let's implement that. And now we are producing a generic package, which becomes a little bit more interesting. First of all, our generic parameter takes on another generic package. Remember, this is what I warned you about. This is the messy part, which becomes large and big and professional. And you have now a queue instance, which I hand over as a generic parameter. So I insist that in order to instantiate this thing, you first have to have instantiated anything which has QPAC abstract and hand this instance over to me. What is QPAC abstract again? QPAC abstract is this thing, which is generic in itself. So the first step is I take this one, I give this one a concrete type, because at this point the elements are still generic. So the first stage, I nail down the element type. And this is still an abstract package, but it already has a type. It doesn't have any operations yet. I hand over this package and I know my type. Then I can define a protected type, which is a new interface. So I now instantiate this actual interface, in this case with a protected type. I have to explicitly say that these two operations are overriding, and I can add a few more for hobby on the side. Okay. The implementation doesn't change. This is still the same implementation as you saw before, but the framework is quite different now. So how do you use that? You're instantiating, this is how the sequence in which you have to instantiate that. First you instantiate your abstract package. In this case I instantiate that with a character type. And then I take the package as a whole and I use that to instantiate the QPAC, which I can then actually use with all the operations in it. So multiple stages where I can decide where to go, what type do I want to use, what implementation do I want to use. You do this in multiple stages. Yeah?
On the previous slide, you changed the EQ and DQ to entry. Also, I responded for that for the specification.
Yeah.
You have the interface and procedures. So
Yeah.
are you just overriding the name or the way, like how it's called?
Yeah, that looks a bit inconsistent because in abstract world you just define this as a procedure, and here it becomes a little bit more specific, and you can actually implement this abstract synchronized procedure here with an entry.
So you're overriding the name of the...
Well, it's the methods still have to fit somehow, and they do in this case. Yeah.
Entries are subclass of procedures, or?
No, not in those words. Not really. Subclass is a strong term here. I wouldn't use quite that. Okay, so this was the fun part of instantiating all that. What can I do with that? Now I can declare a new type, which is a Q class, which gives me access to all Q interfaces I can imagine. Okay. Whatever that means. We'll see that in a second. Then I define two tasks, which I call Q holder and Q user. And the important part, the syntax I'm not showing here, I could have these two tasks now actually on different ends on the planet. They could actually be on different partitions. They don't have to be on the same partition on the same computer. Okay. So what do I do now for the Q holder and the Q user? Those are two different tasks. Keep in mind they could be very far apart. Both of these tasks are defining now a local queue, which is a new protected queue. And I'm now sending over this instance to another task. Ooh. Interesting. That's already a bit of a mind bender. You're sending this to another task. What does this other task do? This other task can now use the queue which it received via message passing from the other end of the planet, and it can use its own local queue. And both are syntactically looking exactly the same. Because we have now our abstract dispatching system in full operation, and we can use now dynamic dispatching to what kind of implementation we are actually running behind that, and specifically on which planet this implementation runs. The dispatching to which continent and planet we have to dispatch to is now done by the Ada runtime for you in the background. And that's a fairly complex dispatching operation. In the case of local queue, NQ, what's the code which is behind that? Well, it's a local lock, some local semaphore which is used by the runtime someplace, and some protected object. No big deal. What's the code which we expect for the remote queue? The code which is produced there depends a little bit where this other computer is. If it's somewhere else on the network, what do you expect to happen?
Serialize it somehow?
You have to serialize it. You have to tunnel it through a network. You have to make sure that the architectures are taken care of. You have to show how big my endian is on one side, how little my endian is on the other side. And you have to transfer this accordingly. That means you don't. It has to all happen somewhere here by the runtime environment. And using those kind of dynamic dispatching facilities, this is the point I'm trying to make here, can be extremely powerful, but you have to be careful what you are calling for, what you are asking for. If you ask for dynamic dispatching, it will give you that, and it can give you very powerful operations, but you have to be aware what is actually happening at runtime to your system here. Cool. And just that. Okay. Make some sense so far? That was a bit of a rougher one, yeah.
What does the all keyword?
The all keyword. It's another funny renamer. The all keyword is dereferencing. Nothing else. It's just .all. There is a bit of a detail in a .all dereferencing means you have actually a standard C-style dereferencing, which means you can read or write with this one. You also have the possibility to restrict dereferencing, that you have only an immutable access, or you have only an immutable access to via your pointer. So you can provide a pointer to somebody else, so you can use that pointer to access my data structure, but don't fiddle with it. Just looking, right? And if you dereference this with a .all, that means you can read and write on it as well. Okay, so that's a bit more detailed. But here in that context, there's the dereferencing syntax. Where do I have a .all on that one? Right, for the dereferencing of that access type. Yeah, okay. Let's have a look how it's defined on the slides before. Here, it's defined as an access. And it's defined here as an access all, which means if you use that type, you can read or write on this other data structure. If you only define this as the type Q class is access Q interface class, you couldn't manipulate the whole thing, you can only read from it. So that I could only use that one to use the function calls into my protected object, but not the side effecting calls. Does that answer your question? Cool. Okay. So far so easy. That's comfort feature, nice feature, which is quite commonly used also. Yeah.
How do you run that task?
You need to have throw a little bit more configuration syntax at Ada to define where your task is actually running. This is a syntax which is outside of what you have here.
Yep.
Yeah. Okay. So now for defining entry families. Entry families is the effect when you want to define points where you can call, but assuming, for example, you want to define a server which has tons of TCP/IP ports, and you don't want to actually write an entry for each individual one. You want to say, I want to have open ports from port 25 to port 30, and I want to have, please give me 6 entries for that. This is called an entry family, and you can do this syntactically just by writing it down once, and you get immediately 6 entries instead of 1. Just syntactically quite convenient, easy to do. How does that look? Syntactically, you have, let's skip the generic part. Syntactically, you have now an enumeration type or discrete type as an additional element in the definition of that one. That means my entry DQ is actually not one DQ, but I have as many DQs as my Q enumerator would give me. I use this here as an implementation that you have a queue where you can have one NQ operation, but you can read this out from multiple tasks at the same time. If you want to have an implementation, for example, of a broadcast messaging system where you put something into a queue so that everybody can actually take this out, but you want to make sure that everybody takes it out exactly once. So from the semantic of all of your clients, this looks like one queue. You want to simulate that for your clients. It looks like they're all reading in their own queue, while de facto you're only storing it once, and you keep track in the background who has already read my information and when can I actually get rid of it because everybody has read it now. But from the perspective of a client, it looks like you have 5 different DQ operations on 5 different queues. This is what you want to simulate with that. So, the data structures is now a little bit more interesting to do that. Anything fancy on that one? Not really. Maybe the one thing which is worthwhile to note is we have in the third, fourth line here, readout is an array of Boolean, and then I define some constants which are whole arrays as a constant, and I can instantiate as a constant. Of course, I have to give it a value, and I instantiate those whole arrays in just one go by saying all entries in that array are supposed to be true, or all entries in that array are supposed to be false. And you can also do this, of course, one by one. And say the first one is true, the second one is false. Yeah, that's a bit of a simplistic version. You do these things usually for much easier readability later. If you want to quickly check whether all of my array elements are they all true already, then you just have a comparison. My current array equals, what did we call this? All red. Much easier to write than actually writing a for loop every time you want to check something like that. You just leave this to the language to do that for you. And now, how do you formulate these DQs so that it will actually translate into many different DQs? You give it an extra parameter for Q in NQ, and you can also use that in the predicates which are going with that entry. And what I express here is you want to DQ from this specific one if this specific Q is not empty. I have to carefully formulate what that means, that this specific Q is not empty. And you can also make it dependent on the state of other entries. And here, in this case, you make it dependent on is the number of processes which are waiting on NQ 0. How many processes are waiting on this other task at the moment? If there's nobody waiting on this other task, I'm serving this one. What do you implement with that? What's the semantic of that? It's already on screen. Okay. So for those who are looking a little bit ahead, what you implement by that one is you actually give de facto priority to the entry, to the NQ entry. Because you have a predicate on all of the DQs which says if there's anybody waiting on an NQ, on my NQ, then my predicate is false. It means you automatically close all the DQs the moment anybody is waiting on an NQ operation. I know it's late. I know it's a little bit concurrent, a little bit advanced. I know. Do you think you will be getting that? You look too confused for this time of the day. Okay, let's make it more practical. I want to have a flight controller, like you have been doing a million times in your life. Using a new flight controller, and I have now defined a set ready, set, go, and different flight states, takeoff, cruising, and landing. I instantiate my QPAC protected now with the elements which I want to store there is ready, set, go. And I have a queue enumeration, which are my flight states. And I can send this now to all of these queues simultaneously. Queue size is only 2. Don't need more than that. Yeah, that's just the implementation of this whole thing. And I can use that by having an aviation module which waits for a specific flight state to become active. Okay. This is where I provide that. This is where it goes into the queue. Well, this is how I use it in the end. Okay, this is leave this a little bit to your entertainment to look into that more carefully, because we're running out of time at the moment. And because this was only the first language I wanted to talk about, there's a whole bunch of languages which we will talk about on Friday. And those languages are not all as comfortable and nice for you as you enjoy programming in Ada. Sort of. They will be synchronous programming languages, for example. It's the first one which we do on Friday. Synchronous programming languages. These programming languages are beautiful. They're assuming something fantastic. They're assuming that no operation will ever take any time. Isn't that wonderful? And on Friday we will discuss why this actually makes sense. Thanks, guys. Have a good evening.